Okay, so let's dive into this. Imagine you're looking out at the very early universe, right? Maybe just a few 100 million years after the Big Bang. For ages, the thinking was, well, you would see something kind of smooth, like a fog almost. A bit lumpy. Yeah, exactly, like a slightly lumpy fog, just gas slowly clumping up because of gravity.
But, well, that's not really what we found, is it? Our universe, it isn't just slightly lumpy. It's structured into this vast network we call the cosmic web.
Right.
Think of it like a giant interconnected system. You've got dense knots of galaxies, long, thin threads connecting them.
And in these massive empty spaces in between.
Huge empty spaces.
Yeah, it's definitely not smooth. It's incredibly structured and honestly kind of surprising when you first see it laid out. What always gets me are those empty bits, the voids. The sources we read said they take up, what, over 80% of the universe's volume?
That's right, over 80%. And it's not just that they're empty, it's how empty they are and how sharp the edges seem to be.
Sharp edges.
Yeah, the density drops off really fast, maybe by a factor of 10 or more compared to the filaments next door. And that boundary, it's surprisingly, well, crisp.
Huh. Right. And that must have been a shock when they started mapping this stuff. I remember reading about the Boothes void. They called it the Great Nothing.
That was a big one, yeah, back in 81.
It's like 250 million light years across. Massive. You could, in theory, cram thousands of Milky Ways inside it.
Easily.
But they looked and found, what was it, 60 galaxies? Maybe?
Something like that, yeah. Vanishingly few.
And that discovery just hammered home that the universe isn't statistically smooth like, a simple gas. It's got this dramatic large-scale architecture.
So the big question is, okay, how did this structure actually form? The standard explanation, the one you'll find in most textbooks, is the lambda cold dark matter model. CDM for short.
Lambda CDM, right?
Yeah. And it's basically a gravity-only model. The core idea is that tiny density fluctuations back in the early universe, they grew over billions of years. Gravity just pulled matter together, slowly building structure from the bottom up.
Small clumps merge, make bigger clumps, that sort of thing.
Exactly. Bottom-up formation.
But, and this is a big but, this model needs things we can't actually see, right? To make gravity strong enough on its own.
Precisely. HECDM requires huge amounts of, well, something called dark matter. Invisible stuff that only seems to interact through gravity.
And there's supposed to be a lot more of it than normal matter.
About 5 times more than all the protons, neutrons, electrons, the baryonic matter that makes us and everything we see.
Wow. Okay, and it also needs dark energy, doesn't it, to explain why the universe's expansion is speeding up.
That too. So you've got dark matter for structure, dark energy for expansion. It's a framework built heavily on these theoretical components.
So this picture was dominant. Slow, bottom-up, gravity-driven, needing dark matter. But then, telescopes like the James Webb Space Telescope came online.
And JWST gave us this incredibly clear view, looking way back towards the beginning.
And this is where it gets really interesting and maybe a bit problematic for CDM.
You could say that, yeah. JWST started finding these surprisingly big, mature-looking galaxies. And supermassive black holes, too, already formed just a few 100 million years after the Big Bang.
That seems fast for a slow bottom-up process.
Exactly. JDDM, with gravity working slowly, struggles to explain how such massive things could assemble that quickly. It just doesn't seem to have enough time.
And it's not the only issue, is it? I mean, JDDM has had other nagging problems for a while.
That's true. Things at smaller scales, like explaining the dark matter distribution right in the center of galaxies, that's the cusp core problem.
Okay.
Or why we don't see as many little dwarf galaxies orbiting big ones as the simulations predict the missing satellites problem.
Missing satellites, right.
And then you get these weird galaxies like DF2 and DF4. They look like they barely have any dark matter at all, which is, well, awkward for a model that relies on it so heavily.
So, okay, if gravity plus dark matter isn't quite cutting it, or at least not fast enough for the early universe stuff,
yeah,
what else could be going on? The sources we looked at, they bring up this really fascinating alternative idea. They call it the blowtorch theory.
Yeah, the blowtorch theory. It offers a completely different perspective and active explanation.
And active. How so?
Instead of just passive gravity slowly pulling things together, the main idea here is that powerful jets blasted out from supermassive black holes very early on, driven by electromagnetism, not just gravity, actively shaped the universe's structure.
Like cosmic blowtorches literally carving out space.
That's the analogy, yeah. These jets would push matter away, creating those huge low-pressure voids we see.
Okay.
And at the same time, they'd lay down magnetic field lines. These lines would then become the pathways for the filaments, guiding matter.
Huh. So the jets do both clear the voids and set up the filaments.
That's the core concept. And here's a really crucial point the material emphasizes. This active process, powered by these black hole jets, could potentially explain the structure we observe using only the baryonic matter.
Only the normal stuff. The protons and neutrons.
Yeah, the stuff we can actually see. The theory suggests you might not need those vast amounts of hypothetical dark matter, at least not to explain this large-scale structure formation.
Wow, okay. That is a fundamental shift. No dark matter needed for the cosmic web itself.
Potentially, yes, for this specific problem.
Right, so this is what we need to unpack in this deep dive then, this blowtorch theory. We need to get into how it supposedly works, what evidence supports it, how it really stacks up against the mainstream CDM view.
And what it implies about the universe's history, right? If it wasn't just passively falling together, but actively sculpted.
Exactly. Looking at the cosmos, maybe less like a rock passively eroding and more like, well, something actively built. Or maybe even grown.
It's a very different picture.
Yeah.
So where should we start? Maybe dig into that cosmic web structure a bit more.
Good idea. The sources break it down nicely. You've got the really dense spots, the nodes. Those are the galaxy clusters and superclusters.
Right. All crammed into less than 1% of the total volume. Incredibly dense.
Then you have the filaments, like cosmic bridges, connecting those nodes, made of gas and galaxies.
They take up maybe, what, 10 to 20% of the volume?
That's something like that.
And then the rest. That huge 80% plus, that's the voids, these incredibly empty regions.
It helps to think of analogies, maybe. The sources suggested like a brain's neural network, nodes and connections.
That works. Or like a map of a country, the big cities are the nodes, the highways are the filaments.
And most of the map area is just empty land in between.
Exactly. That's the voids.
That map analogy clicks for me. You notice the cities and roads, but the space between them is actually most of the area. And that's what was so surprising. Not just that voids exist, but their sheer scale. And like you said, how sharp the edges are, almost like hitting a wall, density-wise.
Yeah, that sharp transition is hard to explain with just gravity over billions of years. Gravity tends to smooth things out, which kind of brings us back to CDM and its focus on gravity. Why did gravity become the go-to explanation for cosmic scales? I mean, electromagnetism is way stronger, isn't it, at short range?
Yeah, that always seemed a bit weird to me, too. It holds atoms together. It's incredibly powerful.
It is. But the traditional thinking was, well, on large scales, in a supposedly random early universe, positive and negative charges would mostly cancel out. Electromagnetism would neutralize itself.
Ah, okay, so it wouldn't add up over large distances.
Right. Whereas gravity, it's always attractive. Always adds up. More matter, more gravity pulls in more matter. Simple and additive.
So gravity seemed like the only force that could really build structure from those initial tiny lumps.
That was the reasoning. So they built these gravity-only models, but then when observations showed structures were bigger, formed earlier, and had these sharp void edges, the models didn't quite match, using only the visible matter.
They needed something extra. A patch.
Exactly. And that patch was dark matter, introduced primarily as this invisible stuff that provides extra gravity. Enough gravity to make structures form faster, make galaxies spin the way they do, and explain some features in the cosmic microwave background radiation.
The CMB, that echo of the Big Bang.
Right. Dark matter helped fit the details there, too.
But the sources we read seemed a bit skeptical about using one theoretical fix, like dark matter, for so many different problems.
Okay.
Because you can kind of tweak its properties, right? Since you can't see it directly.
That's the potential issue, yeah. You look at something like the bullet cluster, and the observations suggest dark matter has to be cold, slow-moving, and collisionless, just passing through itself.
Yeah.
But then you look at other things, like the train wreck cluster, and some argue the dynamics there imply dark matter might need to be a bit warmer, or maybe even interact with itself slightly.
So its properties seem to change depending on what you're trying to explain.
It can sometimes look that way. And if the fundamental nature of your key ingredient seems flexible, it raises questions about whether it's the full picture.
And then the model seems to need more dark stuff added over time. Dark energy was first, but the sources mentioned things like dark flow, dark radiation, even dark fluid with negative mass.
Yeah, as more discrepancies pop up, sometimes more dark components get proposed. The sources compare it to adding epicycles in old astronomy, adding more complex circles to make the model fit the data, rather than finding a simpler underlying principle.
You reminded me of that quote, with 4 parameters, I can fit an elephant.
And with 5, I can make him wiggle his trunk. John von Neumann. Yeah. The suggestion is that CDM, with its adjustable parameters and complex simulations, might become too flexible. It risks being able to fit almost any observation after the fact, which isn't the same as predicting it beforehand.
And the sources were pretty pointed about those big computer simulations of cosmic structure. For a long time, they basically just simulated the dark matter's gravity, right? Ignoring the normal matter entirely.
Yes, for simplicity, often the baryonic matter was left out, treated as almost insignificant for the large-scale skeleton. Newer simulations do include it, which is much more complex. But the critique remains that they often involve a lot of subgrid physics, basically, tuning parameters for things like how much energy black holes pump out, or how fast stars form until the simulation looks like the observed universe.
So it's less predicting the universe and more replicating a picture?
The sources argue it can sometimes feel like extremely expensive CGI, tuning a model to match an outcome rather than deriving the outcome from first principles. It can seem like the theory is often playing catch-up, adjusting itself when new data, especially from the early universe, doesn't quite fit.
More reactive than predictive, maybe.
That's the criticism regarding structure formation details. However, we absolutely have to acknowledge ACDM's major predictive success.
Which was
the cosmic microwave background. It correctly predicted the detailed pattern of fluctuations, the peaks and troughs in the CMB power spectrum, related to sound waves in the early universe. Satellites like WMAP and Planck measured it precisely, and C2DM nailed the predictions. That was huge.
Okay, so it definitely got something very right.
Absolutely. It cemented its place as the standard model for a reason.
The sources also briefly mentioned MOND as another alternative, modified Newtonian gravity.
Right. MOND takes a different approach. Instead of adding invisible matter, it suggests maybe gravity itself works differently at very low accelerations, like those found in the outskirts of galaxies.
Modifying gravity itself, not adding stuff.
Exactly. And MOND has its own scoreboard of successes and failures. Models based on it, like the AAST theory, can actually fit those CMB peaks too. And MOD often does a better job explaining the rotation curves of individual galaxies without needing to fine-tune a specific dark matter halo for each one.
So you've got ACDM and MOND, both with hits and misses. But ACDM is way more dominant in the field.
Yeah, the sources kind of hint at a sociological aspect there. Once a model becomes standard, it gets baked into the tools, the thinking, the funding structures, making it harder for alternatives to get equal footing, even if they have strong points. Like a Coke versus Pepsi situation where one brand just has much bigger market share.
Which brings us back to the blowtorch theory. It's not tweaking gravity or just adding dark matter. It's proposing a whole different mechanism.
A completely different physical process for shaping things. And it starts from two key observations we make today, things that seem separate at first glance.
Okay, lay them on me. What are the two starting points?
First, pretty much every big galaxy we examine has a supermassive black hole, SMBH, sitting right in its center. Millions to billions of times the sun's mass.
Got it. SMBHs are everywhere. Real things.
Second, the cosmic microwave background. We talked about it incredibly smooth overall, but with these tiny, tiny fluctuations in temperature and density. About 1 part in 100,000.
The lumps in the early universe. Fog. Okay. SMBHs and CMB ripples. How do they connect?
Okay, here's the pivot. The sources argue that this very smooth early gas, with only those subtle density wiggles from the CMB, is actually not ideal for making the first stars.
Really? Why not?
Because star formation usually needs smaller, denser clumps of gas to collapse efficiently. ACDM assumes gravity makes those small clumps first.
But the blowtorch theory says...
It says that smooth, slightly bumpy gas is actually perfect for something else entirely. The direct collapse of enormous gas clouds directly into supermassive black holes.
Wait, skipping the star formation step, just straight to black hole?
Exactly. The argument is if you have a huge region defined by one of those large, gentle CMB fluctuations, there aren't enough smaller, denser pockets within it to break off and form stars first. The whole vast cloud collapses coherently directly into a single, massive object, an SMBH.
So the supermassive black holes form first. Before stars, before galaxies. That completely flips the standard timeline.
It does. The standard picture is usually galaxies form, maybe stars collide or gas accumulates, and then a black hole grows later. This theory says the big black holes come first.
And not just a few, but potentially all of them.
The theory proposes that essentially all the SMBHs we see the seeds of today, maybe 1 trillion of them across the universe, their initial mass distribution mirroring the CMB fluctuations, formed in this direct collapse mode, extremely early.
How early?
We're talking really early, within the first 100 million years after the Big Bang. Maybe even, the sources suggest, within the first 50 million years.
Whoa. That is incredibly fast. How could they all form so quickly, almost at once?
The sources describe it like a rapid phase transition. Think of a supersaturated cloud, right? It can hang there, stable, until something triggers it, a dust particle, a change in pressure, and then whoosh, condensation happens rapidly across a large area.
Like rain suddenly pouring down, or
And
crystals forming in a solution.
exactly. Here, the subtle density peaks in the CMB act as the triggers. One region collapses, maybe sends out a shock wave, which then triggers collapse in a neighboring region slightly later. You could get cascades of formation.
So it's kind of an argument from consequences. Like, we see these surprisingly early, massive galaxies and SMBHs with JWST.
Right.
And the standard model struggles to make them that fast. So maybe the early universe had to have a mechanism for rapid direct formation, even if it seems unlikely from the standard view. Like, finding carbon and deducing the Hoyle state must exist.
Precisely. Or like Dan Sheckman finding quasi-crystals, they broke the existing rules, so the rules had to be expanded. The universe is showing us an outcome, early SMBHs, that's tough for the standard model, suggesting maybe a different process was dominant then.
And why must they form so early in this picture?
Because that smooth gas environment is crucial for direct collapse on this scale. And it won't last. As soon as the first few SMBHs form and ignite, their jets and radiation will start stirring up the gas, heating it, making it turbulent. That disrupts the conditions needed for further direct collapse into new SMBHs, so it has to happen in one quick early burst while the conditions are right.
Okay, so phase transition. Trillions of SMBHs form directly and very early.
Yeah.
Got it. Then what? How do they become the blowtorch?
Right. Once you have these monsters, their gravity is immense. They start pulling in the surrounding gas like cosmic vacuum cleaners.
Forming an accretion disk.
Exactly. The swirling disk of gas spirals inwards, but it gets incredibly hot, ionized into a plasma, and a key process kicks in here, the Balbus-Hawley instability. It's basically a magnetic effect within the plasma disk that acts like a brake, letting the gas lose angular momentum and fall efficiently onto the black hole.
And these black holes would be spinning super fast, right?
Yeah.
Because they collapse from huge clouds that had some rotation.
Absolutely. They'd likely form spinning close to the theoretical maximum, the Kerr limit. So now you have a rapidly spinning supermassive black hole bathed in this hot, magnetized plasma disk.
That sounds like a recipe for something powerful.
It's a recipe for a colossal dynamo. The spinning black hole and the plasma generate incredibly strong, organized magnetic fields. These fields then grab plasma near the black hole's poles and accelerate it outwards in two tight focused beams, the jets.
Relativistic jets, moving near light speed.
Near light speed, yeah. Highly collimated, incredibly powerful. The sources mention an example, the Porphyrion jet, which was seen stretching much farther than some theories predicted, suggesting these things can be very stable and sustained.
Okay, so these are the blowtorches. The theory says they then have three main impacts on shaping the universe.
That's right. Three key effects. First, they trigger galaxy formation around the SMBH itself.
How does that work?
As the jet blasts out, it slams through the accretion disk and pushes into the surrounding gas. This creates powerful pressure waves, like shock fronts. These waves compress the gas, creating dense pockets.
Which then collapse to form stars.
Exactly. A cascade of star formation gets triggered in the compressed gas, quickly building up a compact galaxy of stars centered right on the SMBH that created it.
And this connects back to the JWST findings. Because the theory predicted you'd see galaxies forming early and rapidly because of their central black holes.
Yes, precisely. It was an outcome predicted before JWST delivered such striking evidence for exactly that scenario early. Massive galaxies seemingly co-evolving with their central SMBHs from the get-go.
Okay, effect one, make the galaxy. What's number two?
Carve out the voids. Those powerful, sustained jets firing out from trillions of SMBHs across the early, dense universe effectively push matter out of huge regions. They inflate vast, low-pressure cavities.
Like blowing bubbles in the cosmic soup.
That's a great analogy. We see smaller versions today, right? Like the Fermi bubbles above and below our Milky Way center, or the huge cavities jets have blown into the hot gas in galaxy clusters like Able 496. You even see nested cavities there, suggesting repeated jet activity.
So the idea is these early jet-blown bubbles expanded and merged.
Exactly. They'd inflate, push into each other, merge like soap bubbles joining together. And remember, the universe itself is expanding. So a cavity formed when the universe was, say, 120th its current size would stretch along with space. It would grow 20 times wider, meaning its volume increases by 20 cubed, 8,000 times.
Wow. So tiny early bubbles become the enormous voids we see today. And the sources said this explains their kind of irregular shapes, like balloon animals.
Yes, the often non-spherical shapes are seen as relics of these merged electromagnetically defined bubbles. And crucially, that electromagnetic origin explains the sharp boundaries. Gravity alone would struggle to maintain such a steep density gradient over cosmic time, but the magnetic pressure and containment at the edge of the jet-blown bubble can create and hold that sharp edge.
Okay, galaxy formation, void carving, third impact.
Laying down the magnetic fields and forming the filaments. As the jets propagate outwards, they carry magnetic fields with them, stretching and amplifying them. These organized field lines become the scaffolding for the filaments.
Like creating magnetic highways.
Exactly. Ionized gas, plasma, doesn't like to cross magnetic field lines easily. It prefers to flow along them. So these jet-generated magnetic fields act like channels, guiding gas and matter between the voids towards the nodes.
So the filaments are basically the magnetic ghosts of the jets.
That's a good way to put it. The faint fields we detect, even inside voids, are seen as remnants of the jets that clear them out. The stronger, more coherent fields along the filaments are the remnants of the main jet channels, acting like cosmic plumbing, guiding the flow.
And this magnetic channeling explains the sharp boundary, too. The density difference between filament and void.
Yes, that abrupt tenfold density change is much easier to maintain if you have magnetic fields helping to confine the plasma within the filament, preventing it from just smoothly spreading out into the void over billions of years, which is what gravity alone would tend to do.
So just to recap the blowtorch idea, early SMBHs at jet sets make galaxies, carve voids, and lay down magnetic filaments. And this whole structure, the theory claims, can arise just from the normal baryonic matter being pushed around.
That's the core argument, yes. You don't necessarily need the extra gravity from dark matter to explain the existence and shape of this large-scale structure. The electromagnetic forces from the jets are doing the act of sculpting.
Which brings us back to that critique of dark matter as maybe being asked to do too much. The sources use this phrase, the single variable fallacy, or the miasma illusion.
Right, miasma, the old idea that bad air caused all sorts of different diseases.
Like cholera, malaria, the plague.
Yeah.
All blamed on miasma.
Until we discovered the actual diverse causes. Bacteria, viruses carried by mosquitoes, bacteria carried by fleas, etc. Each needed a specific explanation.
So the analogy is, maybe we're asking dark matter to be the miasma for cosmology. A single invisible explanation for structure formation and galaxy rotation and cluster dynamics and CMB details.
When perhaps these are distinct problems needing distinct, possibly sophisticated physical explanations. The blowtorch theory aims to provide that specific, sophisticated explanation for the structure formation part, using known physics like electromagnetism and black hole jets. It argues it can do this job whether or not dark matter exists or is needed for other problems, like galaxy rotation curves.
Okay, so what's fundamentally new here? People have talked about black hole jets influencing galaxies before.
True. The key novelty, as the sources stress, is the combination and the timing. The idea that all SMBHs form first, via direct collapse, in a universe-wide early phase transition before most stars and galaxies, and that this initial population is the primary engine that actively carves out the entire cosmic web, voids and filaments.
So it's not just jets influencing things later, it's jets creating the large-scale environment from the very start.
Exactly. While the possibility of direct collapse SMBHs was explored by researchers like Natarajan, Loeb, Heyman, Brahm, Voluntari, and others, it was often seen as a niche or rare pathway, not the dominant formation mechanism for all SMBHs, and not explicitly linked to carving the entire void filament structure in this way.
And this claim they form first via direct collapse is testable. falsifiable.
Absolutely. If JWST or future telescopes find clear evidence of large populations of stars or galaxies forming significantly before the first SMBHs appear, or if they find SMBHs predominantly forming through other means later on, then this core premise of the blowtorch theory is in serious trouble. But the sources say the current JWST data showing those very early massive galaxies tightly linked with their SMBHs is actually very, very encouraging for this picture.
Now, this blowtorch mechanism, it doesn't exist in a vacuum, right? The sources mentioned it's part of a bigger idea called cosmological natural selection.
That's right, CNS, sometimes referred to as the eggiverse theory, contrasting it with the passive rockiverse picture of CDM.
Eggiverse versus rockiverse. Okay, what's the core idea of CNS?
It originated with physicist Lee Smolin. His radical idea was, what if universes can reproduce? And what if they do it via black holes?
Universes reproduce. How?
The hypothesis is that when a black hole forms and collapses, it might not just end in a singularity, but could trigger a bounce, essentially creating a new region of space-time, a new Big Bang, maybe inside the black hole from our perspective, but effectively a separate child universe.
Wow.
And here's the evolutionary twist. Smolin proposed that the fundamental constants of physics, the strength of gravity, the mass of the electron, things like that, might change slightly, randomly, in each new child universe.
Like genetic mutations.
Exactly like mutations. So if universes reproduce via black holes and their physical parameters can vary slightly, then universes with parameters that happen to be good at making more black holes will have more offspring universes.
Natural selection for universes. Selecting for a maximum black hole production.
Precisely. A kind of cosmic Darwinism. Over vast amounts of time and potentially infinite reproductions, the parameters of the universe would evolve to become highly optimized for making black holes.
And these child universes, they don't cost energy.
The idea is they are free energetically. The positive energy of all the matter and radiation is perfectly balanced by the negative potential energy of gravity, so the total net energy is zero. This allows for potentially infinite reproduction without violating energy conservation. Smolin's original model focused mainly on stellar mass black holes as the means of reproduction.
But the sources we read expanded on this.
Yes, they propose a more detailed three-stage model for how universes might optimize black hole production over their evolutionary history.
3 stages. Okay, what's stage 1?
Stage 1 is the oldest, most fundamental, conserved reproductive mechanism. That early, rapid phase transition leading to the direct collapse formation of trillions of supermassive black holes across the universe. This is the process driving the blowtorch theory we just discussed. It uses only a fraction of the initial gas, but ensures the universe reproduces right from the start.
Okay, stage 1. Early, direct collapse, SMBHs. Got it. Stage 2.
Stage 2 builds on stage 1. The SMBHs and their jets shape the remaining gas into galaxies. These galaxies then form vast numbers of stars. When massive stars die, they collapse to form stellar mass black holes.
Ah, the normal way we think black holes form.
Right. This stage is more complex. It requires galaxies and stars to form first, but it's much more efficient in terms of the number of black holes produced per unit of gas consumed compared to stage 1. So it's a more evolved, more productive pathway that's also conserved.
Makes sense. More steps, but higher yield. What's stage 3?
Stage 3 is potentially the most evolved and hypothetically the most reproductively prolific stage, technologically produced small black holes.
Wait, technologically produced? Like by aliens?
Or by us, or any sufficiently advanced technological civilization that might arise. Here's the thinking. Stage 2 involves stars fusing light elements into heavier ones, metals to astronomers, and spreading them through supernovae. These heavy elements are needed to form rocky planets, moons, maybe other exotic objects like stanets, planets around brown dwarfs, or plumes, moons orbiting rogue planets.
Okay, building the materials for planets and life.
Right. These environments allow for complex chemistry, which can lead to biology, intelligence, and eventually technology. And what's the most efficient way theoretically possible to extract energy from mass?
EMC squared,
Yeah.
converting mass directly.
Exactly. And one hypothetical way to do that with near-perfect efficiency is to create and evaporate tiny black holes. So stage 3 envisions advanced civilizations using technology to convert matter into energy via artificial black holes, perhaps for power or other purposes. This process could potentially create vastly more black holes per unit mass than even stellar collapse.
That's a mind-bending idea. So stage 3 requires a long-lived universe, heavy elements, planets, life, technology.
Yes, it requires billions of years of cosmic evolution, multiple generations of stars building elements, and stable environments for life and technology to develop. The blowtorch theory, driven by stage 1 SMBHs, creates the galaxies, stage 2, which then set the scene for the possibility of stage 3.
So the Eggerverse theory views the whole structure and history of the universe, the web, the galaxies, the elements, as being shaped by this multi-stage drive to maximize black hole production.
That's the core idea. And this evolutionary lens, the sources argue, can make sense of features that might otherwise seem arbitrary. Think about stage 3 again, needing heavy elements and long timescales. That requires careful management of gas within galaxies. You need gas enriched by previous star generations, metals, to be slowly funneled back into stellar nurseries over billions of years to form new stars and planetary systems. Where do we see that happening?
In spiral galaxies, like our Milky Way, with their spiral arms, ongoing star formation.
Exactly. Spiral galaxies seem almost perfectly structured for this long-term, multi-generational process of element building and star formation, essential for stage 3. Now, contrast that with elliptical
The
galaxies.
big, round, reddish one.
Yeah, they make up maybe 10–15% of massive galaxies. They tend to be spherical or football-shaped. They had one huge burst of star formation very early on, used up or blew out most of their gas, and now have very little ongoing star formation. They're red and dead, mostly.
So they're not good candidates for stage 3.
Not really. They burned bright and fast, but didn't set themselves up for the long game of element enrichment and sustained star formation needed for complex life and technology. The sources speculate. What if elliptical galaxies are like evolutionary relics?
Like relics of what?
Maybe vestiges of an earlier evolutionary phase of the universe, perhaps one optimized primarily for rapid stage 2 production, just making as many stars and stellar black holes as quickly as possible before the parameters shifted, or the system evolved to favor the more complex long-term stage 3 pathway that requires spirals.
Whoa. So different galaxy types might represent different evolutionary strategies or epochs. That's a wild thought.
It is. The sources even touch on more speculative traces potentially hidden in fundamental physics, like the heavier cousins of the electron, the muon, and the tau particle. Why do they exist?
Yeah, they seem like heavier copies that decay quickly.
The theory speculates maybe they were the relevant particles in the more energetic physics of stage 1, direct collapse, or stage 2, stellar cores, before the universe's parameters settled on favoring the lighter, stable electron, which is absolutely crucial for the chemistry needed for stage 3 life and technology.
So even fundamental particles could be fossils of cosmic evolution.
It's a highly speculative idea, but it fits the paradigm. Another example mentioned is the CNO cycle in stars' fusion process using carbon, nitrogen, oxygen. It's key in massive stars, stage 2. But those same elements are also the basis of organic chemistry and life, stage 3. An exaptation, maybe a feature evolved for one purpose, later co-opted for another.
It paints this picture of the universe as, well, not just static background, but a deeply interconnected, evolving system. Messy, maybe transitional, but with direction.
Precisely. Not a random collection of stuff governed by arbitrary laws, but perhaps a system fine-tuned by evolution for complexity and reproduction, where we are, in a sense, part of its ongoing development and even self-awareness.
Okay, this is fascinating framework. But a scientific theory needs to be testable. What are the specific, concrete predictions the blowtorch theory makes that could potentially prove it wrong?
Right. The falsifiable tests. This is crucial. Let's list them out.
Okay, hit me. Prediction 1.
The absolute core prediction. Supermassive black holes form first, before the bulk of stars and galaxies. And they form very early, definitely within the first 100 million years after the Big Bang, maybe even inside 50 million years. Finding widespread star or galaxy formations significantly before these first SMBHs would be a major blow.
Testable with deep JWST fields and future telescopes.
Okay.
2.
Those earliest SMBHs, formed from direct collapse of huge clouds, should be spinning extremely fast, near the theoretical maximum, the Kerr limit. Measuring the spin of the most distant quasars, which are powered by SMBHs, is a key test. Slow spins would be problematic.
Prediction 3.
The SMBHs actively generate the stars and galaxies around them. The structure of the earliest galaxies should show evidence of being shaped by outflows or jets from the central SMBH.
Okay.
The SMBHs, through their jets, actively generate the large-scale cosmic web itself, carving the voids and laying down the magnetic tracks for the filaments. The structure should reflect this electromagnetic shaping, not just gravity.
Okay, those are about the formation process.
Yeah.
What about other signals?
A huge one. Gravitational waves. That proposed early phase transition where maybe a trillion SMBHs form almost simultaneously via direct collapse, that should unleash a unique universe-filling background of low-frequency gravitational wave.
A gravitational wave counterpart to the CMB's light.
Exactly. The sources call it the popcorn signature. Imagine the sound of trillions of kernels popping around the same time. It would be a stochastic background, a hum characterized by many overlapping signals, starting sharply, the collapse, peaking intensely, and then decaying over maybe a million years or so, all happening within that first 50 million years of cosmic time. Detecting that specific low-frequency gravitational wave signal would be incredibly strong evidence.
Wow. A smoking gun signal found. What else?
There should be a direct statistical link. The size and number distribution of the initial density fluctuations seen in the CMB should correlate directly with the initial size and number distribution of the very first SMBHs formed, before later mergers confuse the picture.
Makes sense. Connects the input, CMB, to the output, SMBHs.
And look for collapse cascades in space and time. When we map the very earliest quasars lighting up, their turn-on times shouldn't be perfectly random. We might see clusters where one quasar ignition seems to trigger others nearby slightly later, maybe due to propagating shock waves from the initial collapse. Non-random clustering in ignition times.
Subtle, but potentially detectable. What about the galaxies themselves?
In those very early high redshift galaxies, look for specific geometric patterns in star formation. Arcs, circles, maybe cones of young stars centered on the active SMBH, showing where the jet plowed into the gas and triggered star birth. Clear morphological evidence of jet-driven formation.
Moving out to the filaments.
The magnetic fields within filaments should be remarkably uniform and highly correlated along the filament's length over vast distances. Not patchy or tangled, but showing a clear directionality inherited from the collimated jet that formed the channel.
And wasn't there something about them being twisted?
Yes, the rifle barrel prediction. Because the SMBHs are spinning, the jets they launch should twist as they propagate, imparting a helical or spiral structure to the magnetic field lines within the filament, like the rifling inside a gun barrel.
And that would affect gas flow.
A helical field would make gas flow very smoothly, with low turbulence. The sources cited the surprisingly smooth gas flow in the Abel 3667 filament as potential evidence. The key test is to directly measure for these large-scale helical magnetic fields in filaments.
Okay, helical fields and filaments. What about the voids?
Several predictions there. Inside the voids, very weak magnetic fields, as expected since matter was cleared out. But at the boundaries, stronger, possibly sheet-like or bubble-like magnetic fields, the skins left over from the expanding jet cavities.
And where voids merge.
You should find seams, topological defects in the magnetic field structure where different bubbles met. Sensitive measurements looking for abrupt changes in Faraday rotation across these predicted seams could map them out. Maybe even faint X-ray or radiosynchrotron signals from shark relics where the bubbles collided.
And the density profile at the edge.
Back to that sharp boundary. The theory predicts a near step function drop in density between filament and void, occurring over a smaller transition zone than standard gravity-only CDM models would predict. Electromagnetic containment holds a tighter edge.
Okay, one more.
A statistical link between the engine and the excavation. Before things get too messy with later evolution, there should be a tendency for the largest early SMBHs to be found at the ends of the largest voids. Bigger engine, bigger hole dugout.
That's a pretty comprehensive list of testable predictions. Seems quite distinct from CDM in many areas.
Definitely. And the sources also suggest this blowtorch CNS framework might, down the line, offer natural explanations for other puzzles too. And things like the weird large-scale alignment of quasar polarization, why galaxies seem to spin preferentially in certain directions, spin asymmetry, maybe even the cuss core and missing satellite problems, galaxy rotation itself, possibly even the Hubble tension.
So not claiming to solve them all now, but suggesting the framework has the potential for sophisticated answers to different problems, rather than needing one miasma fix.
Exactly. It's about opening up possibilities for different mechanisms, solving different issues, all within a potentially coherent evolutionary picture.
Okay, let's just pull back for a moment and really contrast the two big pictures presented here. On one side, CDM. The sources called it the rockiverse.
Yeah. A universe fundamentally made of passive, dead matter, including dark matter, governed by fixed, possibly arbitrary physical laws. Structure arises randomly from initial fluctuations via gravity. Complexity, like life, is seen as basically accidental, a fluke. It's a one-shot universe with no inherent direction or purpose.
Which is the alternative, the blowtorch theory within CNS, the Eggieverse.
Right. Here, matter itself is seen as potentially sophisticated, capable of complex behavior driven by electromagnetism and other forces, not just gravity. The laws might not be arbitrary, but could be fine-tuned through cosmic evolution. Structure isn't random, but actively shaped by processes like the SMBH jets. Complexity isn't accidental, but perhaps a goal or natural outcome of the evolutionary process, potentially linked to reproduction. It implies a universe with history, stages, maybe even purpose.
It really makes you think about that story the sources told about Victor Weisskopf visiting Kitt Peak, asking the astronomers if they ever actually looked through the telescope.
And they said no, they just looked at the data, the models. The analogy being, are we in cosmology only looking at our preferred models, like CDM, and trying to make the data fit? Or are we willing to look directly at the universe, the surprising structures, the early galaxies, the magnetic fields, and ask what it might be telling us, even if it requires a different model?
It's a call to really engage with the observations, maybe with more open mind about the underlying reality. Which story, which paradigm feels like it resonates more with the sheer complexity and, well, structuredness we actually see?
Is it more like a random pile of rocks? Or more like a developing egg, full of intricate processes leading towards a complex outcome?
So, wrapping up this deep dive,
Mm-hmm.
we've explored this really different take on how the universe got its structure, the blowtorch theory. It's an active explanation, early supermassive black holes, blasting jets, carving voids, laying down filament, shaping the cosmic web with electromagnetism.
And it emerges from this broader, quite radical evolutionary framework, cosmological natural selection, the Eggiverse, where the universe itself might be evolving to maximize reproduction via black holes.
A key takeaway is its claim to potentially explain this large-scale structure using only the normal baryonic matter we see, challenging the need for dark matter for this particular job.
And it offers a whole slate of specific, testable predictions, the popcorn signature in gravitational waves, helical magnetic fields, sharp void boundaries, early SMBH spins that seem quite different from standard expectations, and are becoming reachable with new observations.
It really feels like it challenges some core assumptions. Is the universe passive and random, or active and maybe even directed? It forces you to look at the cosmos in a new light.
Suggesting it could be far more dynamic, more ordered, maybe even more purposeful than the standard picture allows, driven by processes and a deep history we're really only just starting to piece together.
Which leaves us with that final thought to chew on, sparked by the sources. If this evolutionary picture holds any water, and if complex life and technology are part of its later stages, what does that imply about us? Are we just a random side effect? Or could consciousness, science, technology be part of how the universe comes to understand itself, maybe even influence its own future evolution? What kind of future does a universe evolving towards complexity and reproduction have, compared to one just fading into cold darkness?